All right, so today we're going to talk about some applications of diagonalization. The first one we're going to talk about is Markov chains or probability transition matrices. And these are nice, very simple models of probabilistic dynamical systems. So in the example here, we have two teams or two states, home and away. And you can think of this as football or basketball or lacrosse. And at each step, you can think of each step as a minute. The current team, whichever team has possession of the ball, may give it up. So for example, the home team is going to retain possession each minute with 90% of the probability, and they're going to give up the ball with 10%. And the away team is going to have similar probabilities. They're in a similar position, but they're going to give it up with 20% of the probability. They're going to give it up, and they're going to retain it with 80%. And so the question we want to ask is, what proportion of the time does each team have possession? Who has possession more? And very quantitatively, by how much? In the long term. All right, so what we're going to do is we're going to model this with a nice simple probability transition matrix and some vectors, and the answer is going to come out by computing an eigenvector. All right, so what's the linear algebra that we need? So we're going to have this vector PT. This is just equal to the home probability at step or minute t in one component, and the away probability at step t. And so this vector answers the question, what's the probability that home has possession at minute t or step t? And also the complement probability. What's the probability that the away team has possession of the ball? So this has some nice properties, this P of t. So this is a non-negative vector. Right, and it adds to 1. What's really nice about this probability is that it's going to have a recurrence relationship based upon the probabilities above. So this 90 and 80, it's going to let us compute this P of t very easily. And that comes into play with a probability transition matrix. So where the probability transition matrix comes into play is the probability at time t plus 1 for the home team, right? Well, the probability that the home team that we get possession of the ball, or we still have possession of the ball, is dependent upon two factors. Either we currently have the ball, so that's with probability P of t, we currently have the ball, PT home, and we'll keep it with 0.9% of the time. So if we keep it right here, with 0.9% of the time, we're going to keep it. Or we didn't have the ball, and we'll get it with 20% probability. And likewise, the probability that the away team will have the ball at the next step is equal to, well, 0.1% of the time, if we have the ball, we're going to give it up. Or if they had the ball, they're going to still keep it with 80% of the time. And so this vector P of t has this very nice relationship. There's a hidden vector in here. This right here should kind of look familiar. That looks like a vector matrix vector equation. And this is just a vector. So we can write this relationship, this system of equations, as a very simple vector. It says that PT plus 1, the whole vector, is equal to this matrix times P of t. So this is the relationship that the probabilities have to obey. They have to obey this relationship. this looks complicated. We would call this linear because this is linear algebra and there's a matrix and a vector. Even though it doesn't seem linear, it seems like it shouldn't be a linear relationship, and it isn't strictly linear. But it obeys this relationship. And what's more powerful about this is that if we start with P0, then P1, so P0 is whoever starts with possession at the start of the game, then P0 would just be this matrix here, which I'm now just going to call a big P, times P0. And then P2, the probability is after 2 minutes, is going to be P times P1, but P1 itself is just P times that probability vector. Oh, that P is not a vector, that's a matrix. There we go. All right, so altogether, this is just P squared times P0. And so down the line, right, inductively, we get that at any time t, the probabilities are precisely the matrix to the t power times the initial vector. So for example, if we started with the ball, then we will get, this is just equal to PT times 1, 0. So these probabilities, this probability vector is just a matrix power times the initial condition. Okay, so how do we answer the question we want to get at? Who has possession of the ball more? Well, that's going to be in the limiting distribution. So the limiting distribution has to be that we want to find the limit as t goes to infinity. But if we take the limit on both sides of the equation here, or more precisely, we're going to take both sides of this equation right here, this says that the limit of pt plus 1 has to be equal to the matrix P times the limit as t goes to infinity of P of t. Well, this is the same limit. Here I pass through the limit. So what this says is, I'm going to abuse some notation here. We can think of this as the infinite vector has to obey this relationship. And this is precisely an eigenvector with eigenvalue 1. So the eigenvector with eigenvalue 1 is going to be indicative of the limiting distribution of our problem. All right, so let's answer a question. So we're going to take our matrix. Here's our matrix right here. And we're going to find the eigenvector with eigenvalue 1. So what's actually fairly interesting is that we didn't compute the eigenvalues. I'm just assuming, based upon the fact that the probabilities say if there's a limiting distribution, there has to be an eigenvalue of 1. We're just going to assume there's an eigenvalue of 1. It turns out for almost all probability transition matrices, there are always going to be an eigenvalue of 1. So we can just compute the eigenvalue of 1. So we're going to subtract lambda or subtract 1 on the diagonal. And we're going to solve p minus lambda I x equals 0. We're going to solve this equation. And so we're going to subtract lambda equals 1 on the diagonal. So that equation is then going to become minus 0.1 and so if we solve this, we put it into an augmented matrix. It's now very clear, right? We can kind of eyeball what's going to happen. We're going to multiply this by 10, and then it's going to eliminate the second row because it's a multiple of the first. So altogether, we're going to get 1 minus 2, 0, 0. So if we reduce it, I did that kind of quickly to save time. We're going to get that. So that tells us that x minus 2y is equal to 0, and y is a free variable in this reduced echelon form. So we have, this tells us x has to equal 2y, and y is equal to y. So the eigenvector is just going to be 2, 1, y. All right, so this is an eigenvector. But keep in mind, this times y means any multiple of it is also an eigenvector. So we specifically want the one that adds to 1. So this probability vector always has to be a non-negative vector, and it has to be the one that adds to 1. So we don't want 2, 1. We want to scale this. But our p infinity needs to add to 1. So we're going to scale it. So we can just take 2, 1 and divide it by the total. And that's going to give us 2/3 and 1/3. All right, so this tells us right here that this is the probabilities that in the long term, who has possession of the ball how often. So if we simulated this, right? We simulate this process right here, we would expect that 2/3 of the time in the long run, home, we would have the ball, and 1/3 of the time the away has the ball. And this is kind of amazing because on the surface, 1/3 and 2/3 don't really show up anywhere in here. It's a quantity you have to solve for. In this two-state example, you can kind of look at, well, the away is giving it up twice as much as we're giving it to them, so we should have possession twice as often. So that intuition turned out to work well in the two-state case. But now you can imagine that if you had 3 or more states, if you were bouncing around between different states, whether that be on an electrical network or what have you, on the internet, going around random websites, you don't just have 2 states, and it's not clear how often you're going to be there. You actually have to solve a matrix equation to figure that out. So this is something you can do, and there's a lot going on behind the scenes here. So for example, the other eigenvalues are telling you how fast this process converges. So the eigenvalue 1 is the limiting distribution, and the other eigenvalues, which turn out to be smaller than 1, are going to tell you how fast this process converges. So there's a lot of eigenvalues and eigenvectors hiding underneath even a simple model like this. Okay, so let's talk about another topic very quickly. We're going to talk about recurrence relations. And these are kind of famous. You've probably played with these a lot. So the most famous one is one that looks like this. And this happens to be the Fibonacci sequence. So how this works is we're going to start with an initial number, in this case, initial 2 numbers. And then what this relationship says is we're just going to take these two, and the next one is just going to be the sum of those. And then A3, the next term in the sequence, is just going to be the sum of the previous two. And so on. And so the main question we want to have is there a formula? Is there an easy formula for AN in general? And more specifically, how fast does it grow? So here we can keep going. The next one's 5, and then it's 8, and then it's 13. And you can keep going. And sure, it's easy just to compute the next one if you have the previous ones, but can we just jump ahead to the 1000th one without computing the first 999? Is this possible? And is there, can we get some sense of how fast does it grow? Does it grow like a quadratic function? Does it grow like an exponential function? Does it grow like some other function we haven't seen about? So we want to answer these questions and get a very definitive formula for recurrence relations like this. The Fibonacci sequence turns out to have some numbers that aren't very nice for an example, so I'll leave that one to you. But let's go ahead and do a different one, and we can answer the same questions about that. So let's take this one. Let's take xn is equal to minus xn minus 1 plus 2xn minus 2. So this one says that we're going to start with, whatever number we start with. So in this case, we're going to start with 0, and we're going to start with 3 for the next one. And so what this says is instead of just adding the previous two, this one says that we are going to subtract the previous one. So we're going to take minus the previous one, and we're going to add 2 times whatever the one before that is. So in this case, we're going to get minus 3. And this is going to be minus 3 plus 2 times 3, and that's going to be 9. All right, so a simple observation might say, oh, there's just powers of 3. That's 0s and 3s and 9s. The next one's probably going to be 27. Turns out that's not the case. We actually get minus 15. So it's not exactly clear what's going on, and we want to figure out what this pattern is. So what we're going to do is we're going to use some linear algebra. So what we're going to do, how we're going to use that linear algebra, is we're going to take this equation right here, and we're going to make a matrix equation from it. And this is kind of a common trick of taking lots of different equations or a system of higher order and making it into a linear system. So what we're going to do is we're going to just put in kind of a dummy variable, xn sub minus 1. And so just like the probability transition matrices, we have a vector here, right? So this vector xn minus 1 is equal to, and this on the right is really a matrix times the vector xn minus 1, xn minus 2. And this matrix is now 1, minus 1, 2, 1, and 0. And so this is the relationship that's taking place at every step, is you're multiplying the previous two members of the sequence times this vector, and then you're getting a shifted version of it. So just as an example, if we started with 0, 3. Then the next one in the sequence is going to be minus 3, 3. And then if we take the next one, we're going to end up getting 9 and minus 3. So it's not a coincidence that this 3 always ends up down here. This is exactly what the matrix is doing. But you'll notice that the top entry is exactly computing the next element of the sequence. So we went from 3 minus 3 and then 9. So this one was 3 and minus 3 and then 9. And if we kept going, we get a vector with minus 15 and 9 in it. But what's powerful about this is that if we just think of this right here, this vector here, let's just call this the vector xn. And this here would be xn. Let's call this first one xn minus 1 because it has the n minus 1. And this one is a vector representing xn. Then we have this relationship that xn is equal to some matrix A times xn minus 1. And so just like the probability example, if we start with x1, right, those are the first two entries times x, this is going to be n minus 1 will give us xn. Right. And this is because you can replace xn minus 1 with a times xn minus 2, and so on until you get n minus 1 copies of it. And you'll end up with a to the n minus 1 times that first vector. So this just says the nth vector is a power times the initial condition. All right, so to get a formula for this, all we need to do is to write A in a very precise way. And this is where diagonalization comes into play. So what we're going to do is we're going to diagonalize A. So let's take our matrix. That's not our matrix. We're going to take our matrix and we're going to diagonalize this matrix. So we're going to diagonalize our matrix, and then we're going to take a power of it. So this is our matrix. So we first need to compute the eigenvalues. And we're going to do that by subtracting lambda on the diagonal and computing the characteristic polynomial. So we get minus 1 minus lambda times minus lambda minus 2. And if we expand this, we will get plus lambda minus lambda squared minus lambda. That should be a minus 2. Sorry, that's a minus 2. And so we can solve lambda minus lambda squared minus 2 equals 0. Well, that's the same thing. If we multiply both sides by minus 1, that's the same thing as just getting lambda squared plus lambda plus 2 equals 0. And this we have lambda plus 2 and lambda minus 1. This is just factoring. All right, so our solutions right now are lambda equals minus 2 and lambda equals 1. So those are our eigenvalues. And now we're going to compute the eigenvectors. And so we're going to take each of the eigenvalues and we're going to subtract that and compute. We're going to solve for lambda equals minus 2. We're going to solve this equation. Oh, -2, that's a plus, okay. Oh, so there's a -2. This should be a +2. There you go. So that's a mistake I'm going to make several times. So we're going to subtract -2, which is the same thing as adding 2. So then now this matrix becomes 1, 2, 1, 2. We're going to set it equal to 0. When we row reduce, that second row is just going to go away. And we're going to get 1, 2, 0, 0, which tells us that x plus 2y is equal to 0. Or in other words, x equals -y. Y is our free variable right here. So y is equal to y, and our eigenvector is -2, 1 times y. All right, for sake of brevity, we can do the same thing. So that's the this right here is the eigenvector for lambda equals -2. And keep in mind, it's any multiple of this. For brevity, I'm just going to tell you that for lambda equals 1, we're going to get xy is equal to 1, 1, y. So this is going to be the eigenvector for lambda equals 1. And now what we're going to do is keep in mind that the formula we had before was that xn minus 1 was equal to a to the n times the initial vector. A to the n minus 1, rather. And so our initial conditions were 0 and 3. So if we can expand out the right side, if we can make sense of the right side, we will actually get a formula for this. And what we're going to do is we're going to diagonalize A. So if we diagonalize A, this becomes SD S inverse to the n minus 1 times 3, 0. And if we expand out what this SDS inverse to the n minus 1 is, you're going to get d copies of it. Sorry, you're going to get n minus 1 copies of d. And so this simplifies to s d to the n minus 1 times s inverse times 3, 0. And we already know what all these matrices are. So we know S, this matrix S right here, is just going to be our eigenvalues. So our eigenvalues, we got -2. For one of them, we got -2 and 1. And that had an eigenvalue of -2, but it's now to the n minus 1. And we also had another eigenvector of 1, 1 that had an eigenvalue of 1. That's also the n minus 1. And we finally have the inverse of this, times 3, 0. And this, if we multiply this out, this is going to give us a formula for xn. Specifically, whatever is in the top, whatever's in the top. This is now going to give us a vector, right? This is a 2 by 2, a 2 by 2, a 2 by 2, and a 2 by 1. So altogether, this is going to give us a 2 by 1 vector. And the top part is going to give us a formula for xn. All right, so let's just multiply these out. So let's calculate this inverse right here. This inverse is going to be 1 minus 2 minus 1 minus 1 times 1 over minus 3. And so we can just multiply this across. So here we're going to get 3 minus 3. But now that's going to be divided by minus 3. So we're going to get minus 1, 1. Then in the next step, we're going to multiply these together. And we'll get minus 2 to the n minus 1 times minus 1 for the top, and 1 to the n minus 1, which is just 1, times 1 for the bottom. And then finally, we can multiply this final step. We're going to multiply this by minus 2, 1, 1, 1. Keep in mind, this is a single number right here, and this is a single number. It's just a function of n. So altogether, what does this give us? This gives us minus 2 times minus 2 to the n minus 1. And there's another minus there. Plus 1 to the n minus 1 times 1 times this one right here. There's 2 1s going around. That's for the top. And the bottom follows very similarly. It's just going to be minus 2 times minus 2 to the n minus 1 plus, this is a plus now. So that's now a vector. And if we simplify this, there's a lot of simplifying going on. These 1s don't matter. And these 2s can kind of pop into this exponent here. I made a mistake. There's no 2 here. That's just a 1. So it's this one right here times this whole thing. But there is a minus. There's this minus right here. All right, so let's simplify everything. So the top's going to be just 2. This minus 2 can go inside. So you get minus 2 to the n, but there's a minus in front. And this is just a 1. So that's the top. And the bottom here is going to be minus 2 to the n minus. It's not a minus. Yeah. You'll get minus 2 to the n minus 1 plus 1. So this is the whole vector. All right, and just like we said, the formula, whatever's on top is going to give us our formula. So there's our formula. So our formula is xn is equal to minus 2 to the n plus 1. And you'll notice that it's always a power of your eigenvalues. And that's not a coincidence. So the only place the eigenvalues, the only place n comes into play in this formula is on this diagonal. So it's, your answer is always going to be some combination of powers of your eigenvalues, which is why eigenvalues are so important. And so let's check this out, right? If we plug in x0, which we know from before was 0, This is minus 2 to the 0. That's just minus 1 plus 1. That's in fact 0. And we can even be more daring. We can try x to the 4th. This is minus 2 to the 4 plus 1. That's minus 16 plus 1, which is minus 15. And sure enough, if we go up to back to where we started this example, we got x4 was minus 15. So this is the generic formula. So every recurrence relation is going to have a formula very much like this. It's going to be powers of its eigenvalues of the corresponding matrix. And this works for almost any recurrence relation, no matter the size or the power. The only wrinkle is it may not work if you happen to have repeated roots. We have to do some other things because those may not be diagonalizable, but otherwise this is good to go and it gives you a way of solving these recurrence relations.